The internet is a critical part of our lives. There's very little we do in everyday life without using it. In this video, I'll introduce you to the computing ideas that underpin internet technology. The internet of today has its origins way back in the 1960s with the development of a technology called packet switching. But before I describe packet switching, I'll describe the world before. In those days, computers were connected using telephone network technology or circuit switching. Circuit switching involves creating a complete circuit from the source to the destination when a call is requested, and shutting down the circuit when the data transfer is complete. With circuit switching, the data is sent in a continuous stream over the same circuit for the duration of the call. Originally, a circuit meant a physical set of wires connecting the exchanges. Each exchange was connected to the next with many sets of wires. And this put a limit on the number of simultaneous connections because each connection between users, either telephones or computers, had to use a single set of these wires. So if you only had 10 sets of wires connecting two exchanges, you could only have 10 simultaneous connections. So that's a bit of a problem. Of course, one advantage of circuit switching is that each data connection has reserved bandwidth because each connection is using that dedicated set of wires. This means that there's a known constant delay for data flowing over the connection. So no glitches when more people start using the network. But also, as I said, this means that you'll have a problem if more than the capacity of the network wants to join. Now, there are also a number of problems with circuit switching. The big one is that the reserved bandwidth is wasted if there's no data being transmitted. Those wires just are idle and you can't make use of them. Also, if there's an interruption to the circuit, then you can't recover from that without making a new call. The technique of packet switching was invented to fix these problems. Instead of sending data as a continuous stream over a fixed circuit that had been set up at the start of the call, packet switching involves breaking the stream of data into small chunks or packets and sending them independently through the network and then reassembling them in the correct order when they get to the destination. These packets don't necessarily all follow the same path or route through the network. They can follow different routes. This means that packets can be rerouted around breaks or congestion in the network, and this is a huge advantage. It gives the network resilience in the face of faults or overloading. Another major advantage is that the data from different connections can share a physical channel, so packets from many different connections flow over the same link. The most common network technology today involves packet switching, and by far the most widely used standards are the internet standards. Even phone calls are now transmitted using this internet technology and don't use the old-style circuit switching anymore. Now, connections between computers fall into two broad classes. There are the local area networks and wide area networks. And a local area network can be as small as your home or as large as a whole campus or even a city. Whereas a wide area network is global and consists of many interconnected local area networks. In fact, the term interconnected networks is where we get the term internet. And both the local area networks and the wide area networks use the packet switching technique to transfer data. The difference comes more in how the packets are routed around the network, but I'll get to that later. Now, the most common form of local area network uses Ethernet technology for the interconnection, and Ethernets come in many forms. So we can have wired Ethernet networks where the computers are connected together and to each other using twisted pair wiring via a router or a switch, as you can see here, or a Wi-Fi network carries the packets using wireless connections. So same idea, except instead of using a wired connection, they're using radio or wireless. And eventually the Wi-Fi access point, of course, does have a wired connection to the network itself, the rest of the network. Now, in both these, in a local area network, in a wired and a wireless network, the data is carried using something called an Ethernet frame. Now, this is just one of these packets I mentioned where they've taken the data stream and chopped it up. But the Ethernet frame, this layout of bits, it's another sort of packet, but it has lots of other information to help get it through the network. So at the beginning, there is a thing called the preamble, a few bytes to get the whole thing synchronized. Then there's a starter frame to tell you where the frame begins, where the packet begins. Then there's the destination address and the source address. Then the length, the overall length of the packet. And then there's a variable number of bytes to give you the actual data that's being carried. In the case of Ethernet frames, it's from 46 to 1500 bytes. And then finally, there's a 4-byte check or checksum cyclic redundancy check, CRC. We'll talk about that in a later video. Now, these Ethernet packets or frames are carried point-to-point only, basically from one physical device to the very next one that it's connected to, either by the wireless or by the physical wires. And the addresses inside this Ethernet frame designate each end of this point-to-point connection. Now, inside the Ethernet frame is some data, and this data is another form of packet, and it also has source and destination addresses. But these source and destination addresses designate the very beginning and the end point of the connection, and the data packets may make many hops along the route to the destination. For each hop, they'll be carried by a different low-level network frame or Ethernet frame. And this illustrates a really important concept in computer networking called layering. Packets are carried inside the packet of the next lower level. At the bottom level, the Ethernet frames go from one device to the next directly, but they carry the packet of data that's then forwarded from one network node to another all the way to the destination. Now, these Ethernet frames or packets, they have addresses inside them because they have to know which particular physical device they're coming from and going to. And in the case of the Ethernet frame, these are 48 bits long and they are unique. They're globally unique. So when you get a new Ethernet device, the manufacturer applies for a block of addresses and is allocated an address from this block for the device they've just constructed. And so every one of these is unique. Now I know in some cases you can actually change this, but that's getting pretty fancy, and the idea normally is that you make these unique. Now the Internet packets, these things which go inside the Ethernet frame, can be much longer than the frame can be. And so typically they are less than or equal to 1500 bytes, so they fit inside a frame, but they can be fragmented and carried in multiple frames. Now, here is the layout of the Internet packet. This is the packet that's carried inside the Ethernet frame. It consists of a header containing the length and other information about the packet, and it has its own source and destination address, and then the actual data. Now there are a number of parts to this. If you look at the very first part of the header, it's got the version number, and the two widely used versions of the Internet packet are IP version 4, which is the majority, and IP version 6, which is slowly being rolled out over many years. There's also the length of the packet, because the packet can be variable length. There is a thing called time to live, which is the number of hops before the packet's discarded. This is to prevent loops occurring accidentally in the network. If it's going round and round a particular set of paths and getting back to the beginning and going again, then you want to stop that. And so you have this time to live or hop count before the packet is discarded. There's also a protocol number which says what the packets that are inside this packet, what protocol they are conforming to. because there are other higher level protocols in the layering. There's a checksum for the packet itself, for the packet header, just in case there are errors. You can check to see if it's correct or not. And if we look at the stack here, you can see that the Ethernet frame is the low level, and the IP packet is carried inside the Ethernet frame, and then there are other layers above that. Now, the addresses are very important inside the Internet packet. They are 32 bits long, or 4 bytes each, and you may have seen them written down as 4 decimal numbers, each in the range 0 to 255, separated by dots. That's a lot easier to write than a 32-bit binary number or hexadecimal number. So we'll come back to this in another video about namespaces. But basically the IP address, this 32-bit number, is very important for working out the route through the network. Now, network services often have many layers where the message is carried inside another message and so on. In the case of the Internet, it looks like this. So far I've talked about the Ethernet frame and which carries the Internet packets. But above that, there are other layers. And we need more than just the Internet packet format to get the data through. The other thing is that as well as the format of these packets, we need an agreed set of rules about what to do with them. What happens if one gets lost, and how you decide where to send it in order to get it to the destination, and so on. And this set of rules is called a network protocol. It tells us how to control the sequence of packets that are exchanged between computers. The network protocols have to be implemented on all the computers on the network. Everyone has to agree. And the Internet has a set of these protocols that govern all the layers. And now a little bit of history. The early Internet packet switching technique was developed by both the British and the Americans at about the same time. The first production network was in Britain, but the system that developed into today's Internet came from the USA. And the Advanced Research Projects Agency, or ARPA, in the US funded a major research project on packet switch networks in the 1960s, at the height of the Cold War. The idea being that since packet switch networks gave the ability to withstand many breaks in the network, they thought this would be very useful if a major disruption occurred, say in a nuclear war. And the first network that was built was called the ARPANET, and it started in 1969. It linked together universities and research centers across the USA. And this diagram I've got here shows you what it was like in 1973. Each one of these symbols was a single computer, so you can see how small the network was. It does span the entire US and over to Hawaii, and it also had, a little bit after this, it had a satellite link to the UK, and there were a couple of computers in the UK. This was in the very early days. In the late 1970s, after 10 years of development, the basic protocols were revised and improved, and at the beginning of 1983, the network switched over to the system that we use today. An extra bit of information about the place I live, Australia. The first internet connection was established in 1989 from Hawaii to the University of Melbourne. The link actually went via Sydney, but the University of Melbourne was the node, and it connected back to NASA in Hawaii. Now, as the Internet protocols and procedures were developed, they were documented in a set of documents called the Request for Comments, usually known as RFCs. This name came from the fact that they were used originally for proposals that eventually became Internet standards, and the standard documentation is still in these documents to this day. Now, they're all online, available at this URL, www.rfc-editor.org, and they're available in various formats, but the traditional standard form is just plain text. So if you're interested, you can go to that website and have a look at them. There are thousands of them now. Also, the development of Internet protocols is done by committees that are open access. Anyone can join the committees that are developing protocols, and it's through an organization called the Internet Engineering Task Force, or IETF. And they have very frequent meetings, several times a year in various parts of the world, where these committees come together physically and work on the protocols. And all the protocols that you now use in the basic internet were developed and are being developed through the IETF. A common requirement in computer-to-computer communication is to send a large message or a stream of data, like a video. We can use packet switching to break up the data stream and send the packets independently, but this alone can have problems. If a packet was lost or corrupted due to a hardware failure, or just electrical interference or something, or there's congestion detected, then the packet might travel via a longer route. And this can cause packets to fail to arrive or arrive out of order. Now, we can detect most of the data errors at the internet packet level using a checksum. But how can we recover when an error like this is detected? So the solution is to create a protocol, another layer on top of the internet packets, the IP packets. And this protocol maintains a sequence number in each packet so that the out-of-order packets can be reassembled in the correct order. And there's also a way of requesting retransmission of packets that have been lost or didn't arrive, or that have errors, and so on. And there's also a way of acknowledging the packets that are received correctly. Now, this protocol, which sits above the IP layer, is called the Transmission Control Protocol, or TCP, and it's commonly called TCP/IP. And this is, in standards terms, what we call the transport layer. The IP layer we call the network layer, and the Ethernet layer is called the data link layer. These are the standard names. Now, above the TCP/IP layer is something I've labeled here as application data, but it's actually more layers, since it's usually data for some application. So, for example, a web page or a video stream and so on, they have their own protocols with message formats and rules for exchanging messages. For the web, for example, we have HTTP, and that's used to request and transfer web pages. And I'll do a video on HTTP in sometime in the future. In this video, I've given a very basic introduction to the concepts and ideas behind Internet protocols. The key idea is layering, and that lets us build services that use services of the layer below and provide services to a layer above. Each layer is specialized and allows the layers above to concentrate on their particular service that they're designed for without worrying about services it depends on. So, for example, the Ethernet frame provides a basic method of getting data from one node to the next, while the layer above, the IP layer, provides an end-to-end but unreliable data transfer. And then above that, we have the transport layer, which provides a protocol to make it reliable. In future videos, I'll talk about how we route the packets through the network in the local area network, but also the wide area network. I'll talk about namespaces and, in particular, the domain name service, which allows us to work out what the IP address is that corresponds to a domain name that you're probably more familiar with. And I'll say a bit about application layer protocols, HTTP, the web protocol, but also SMTP, the mail protocol for transferring mail, and above that again is another protocol called MIME for mail format, for transferring multimedia mail and so on. And lastly, I'll do a video on network security, which is, of course, super important these days. Thanks for watching.